All right, this is Chapter 13, Problem Set 1. Let's start with Problem 17. 17 says, what will an object weigh on the moon's surface if it weighs 100 newtons on the Earth's surface? And then there's some more, we'll get to that in a second. So what will an object weigh on the moon's surface if it weighs 100 newtons on the Earth's surface? So when we talk about the weight of an object, so W is equal to weight, and if you're at the surface of the Earth, you can calculate weight by using mg, where m is the mass of the object, and g is the gravitational field strength. Now, in the textbooks, they always say, oh, the gravitational field strength, g, which is, we know, 10 newtons per kilogram. They equate that to g is equal to 10 meters per second squared. And they assume that those are equal, or that you understand how those are the same and how they're different. And for our purposes, it actually just doesn't matter that much. But this g is that's how you calculate the weight. So if it weighs 100 newtons on the Earth's surface, so for the Earth, we know g is equal to 10. Again, newtons per kilogram or meters per second squared. Again, because they're equivalent in number, it doesn't matter here. So the weight is 100 newtons. That is equal to the mass measured in kilograms times our value, which is 10. And so it turns out the mass is 10 kilograms. And they want to know how much it's going to weigh on the Earth or on the moon. So let's do the moon. On the moon, the g value is 1.6 newtons per kilogram. So the weight, again, mg, would be equal to the mass from here, times 1.6, so it would weigh 16 newtons on the moon. So a 100 kilogram object on Earth only weighs 16 newtons on the moon. Second part says, how many Earth radii must the same object from the center of the Earth to weigh the same as it does on the moon? So this is an interesting problem because they're actually asking a slightly different question here. We know that when we talk about the local weight of an object, we know that it comes from the gravitational force on the object. So little mg is equal to g, big M, little m, all over d squared. So if you want to calculate the g value, near a planet, you can take the planet's mass, and this is the distance from its center. So we're talking about the Earth again. So you want the g value that we're solving for to be the same as that on the moon. And then we're going to solve for d. So in here, we're going to need to know our g value and our m value. So g, universal, 6.67 times 10 to the negative 11. And the mass of the Earth is equal to 5.98 times 10 to the 24th. So if I want to solve for d, we'll solve for d squared. It's easier to write. I'm going to take gm divided by 1.6. All right, the handy dandy calculator. So d squared is equal to 2.5 times 10 to the 14. I'm going to take the square root of that. 1.58 times 10 to the 7 meters. Now that's the distance. But it wants to know how many radii from the center of the Earth. So to calculate that, I'm going to take my distance, I'm going to divide by the radius of the Earth, I had to look up the radius of the Earth, but it's 6.37 times 10 to the 6th, and that's equal to 2.48. So an object would have to be 2.4 Earth radii away from the center of the Earth to have the same gravitational field strength as on the Moon. All right, problem 19. At what altitude above the Earth's surface would the gravitational acceleration be 4.9 meters per second squared? It's a great question. So if I think about the Earth, okay, we know that at the surface, the G value at the surface is, now I'm going to call it 9.8 meters per second squared. Now, we use 10 to make the math easy, but at the surface, right? But that is 1 radii away. The farther out you go, the less gravitational field strength you have. So if you are out farther than the surface, it's going to be less than 9.8. From the previous slide, what we saw was that the local gravitational force, mg, is equal to the universal gravitational force. And so if you want to calculate the acceleration due to gravity, you can take the g times the mass of whatever planet you are, and this is the distance from the center of the planet. So the question says, at what height above the surface? So I want to be like somewhere out here, and we want to know, I might even say altitude. At what altitude above the Earth's surface? So I'm going to say A for altitude above the Earth's surface. So when I write this then, our G value is universal. It's still the mass of the Earth. And what is our D going to be? Well, our D is going to be the R value, which is the distance to the surface, plus the altitude. And don't forget, you got to square the distance. And so now it tells us I want the G value to be 4.9 meters per second squared, which is half this. This is what they're trying to be tricky to say half. So do I have to go a whole radius away to get it to half? And the answer to that is absolutely not, because this is a D squared. If I go 2 times the radius, I'm going to go 2 squared is 4. It's going to be a quarter of it. So let's just go ahead and calculate this out. So I want this to be, well, let me rearrange first. Oh gosh, what the heck was that? So I know the radius of the Earth is 6.37 times 10 to the 6th plus the altitude. Now we're going to have to square this whole thing. And then again, our G value, 6.67 times 10 to the negative 11. The mass of the Earth is they want this to be 4.9. Now, obviously, when you look over here, this is going to end up being some sort of quadratic equation. And we don't need to go through all the math on this. I think that getting the setup is going to be fine. So if I just take one step back, if I square this thing here, I'm going to get r squared plus 2 RA plus a squared, and that's equal to this side here, which is GM over G. And this is going to be a number, this is going to be a number, and then we're going to have to solve the quadratic equation for this one. So this is one of those occasions where it actually may not be super useful to work in terms of variables. So if I go back a second here, let me just go back. This is fine here. It's funny, sometimes working in variables is the easiest way to go, and then sometimes working in variables is not. So let's look at what we have here. So if I take a step back and I just look at this, I know that d squared from this equation here is going to be equal to gm over little g. Now, I can plug in right here. I'm going to do it over here. So d squared is equal to 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. I'm going to divide the whole thing by 4.9, which is what they want. Now, I'm going to put this directly into my calculator, and let's see what result we get. So I calculated d here on my calculator, and I got d to be 9.02 times 10 to the 6th. But here my d is just equal to r plus a. And it's nice because I know both d and r, and I can solve for a directly. So a should be equal to d minus r. So, turns out my altitude is 2.65 times 10 to the 5th. And this number, okay, compared to the radius of the Earth, let's see what this means. So the radius of the Earth is 6.37 times 10 to the 6th. So this means this altitude here would be equal to 0.265 times 10 to the 6th. So it's a small fraction. If this distance is 6, then this extra distance is only 0.26. So it's only a little bit off the surface. Oh, that's totally lies. I just counted wrong. This is 6th. What this is saying is it's about half. So it's another half of radius out there. That's what the altitude is. All right, let's do problem 31. The mean diameters of Mars and Earth are 6.9 times 10 to the 3rd kilometers and 1.3 times 10 to the 4th kilometers, respectively. So let's write those down. So the diameter, use capital T. The diameter of Mars is 6.9 times 10 to the 3rd. Now, that's kilometers. We're going to have to work in meters here in a second. So the diameter of the Earth, 1.3 times 10 to the 4 kilometers. All right. The mass of Mars is 0.11 times the Earth's mass. Okay, so that's an interesting statement. what is the ratio of the mean density, mass per unit volume, of Mars to that of Earth? All right. So the idea is we're talking about the density, so it's mass per unit volume. So the density, so we're going to use rho. This is the Greek letter rho for density. It's mass per unit volume. Now, we can calculate this, right? I could put it and say, oh, what is the mass of the Earth? Calculate the mass of the Earth, calculate the mass of Mars, and do this whole thing. That is a fine way to do this. But I think what they want is what is the ratio of the mean density of Mars to that of Earth. So what we're going to have to calculate here is the rho of Mars divided by the rho for Earth. So I'm going to take the mass of Mars divided by the volume of Mars, and we're going to divide that by the mass of the Earth divided by the volume of Earth. So when you divide a fraction by a fraction, you actually are multiplying by the reciprocal. So this ends up being all right, so what we're going to do is, sorry, I got a typo. We divide this here. It's mass of Mars divided by mass of Jupiter. Mass of Mars divided by the volume of Mars. And then times the volume of Earth divided by the mass of Earth. Now, if we remember back to geometry, volume is equal to 4/3 pi r cubed, which means that the volume is proportional to the diameter cubed. It would change the constant, but it's just a proportionality here. So if I want to do this fraction, density of Mars, density of Earth, mass of Mars times the density of Earth cubed divided by the mass of Earth times the density of Mars cubed. Oh, diameter. These are diameter. These rows are density. So when I look at it here, I have the mass of Mars is 0.11 times the mass of Earth. So I have 0.11 times the mass of Earth times the diameter of Earth cubed divided by the mass of Earth times the diameter of Mars cubed. And we see that these cancel out. I'm going to plug these into the calculator and let's see. So I plugged in the diameters. This canceled, I multiply, and I got 0.74. So the ratio of the density of Mars to the density of Earth is 0.74. So what that means is that Mars is less dense than Earth. It's about 3/4 of the density. All right, rest of problem 31 says, what is the value of the gravitational acceleration on Mars? So we've seen this before. We know the gravitational acceleration is equal to gm divided by r squared, where this could be used on any planet. So if we do Mars, it would be the mass of Mars, and this would be the radius of Mars. And what we're going to do is we're going to compare it. So I know that the gravitational acceleration on Earth, which is 10, or 9.8, is equal to g times the mass of Earth divided by the radius of the Earth squared. Similarly, if I want to do Mars, g mass of Mars divided by the radius of Mars squared. Now, what I like about this problem is I'm going to rewrite this Mars here in terms of the Earth. So g for Mars is going to be equal to g. Now, the mass of Mars here is 0.11 times the mass of the Earth. And if I look here, this is a diameter ratio. And so I'm going to divide to get a ratio, like what is the mass of Mars compared to the mass of Earth. So I'm going to take 6.9 times 10 to the third, I'm going to divide it by 1.3 times 10 to the fourth. And what that tells me is that the radius of Mars is 0.53 times the radius of Earth. And don't forget to square it. So this is 0.11 on top, this is 0.53 squared on the bottom. And so I end up with 0.39 times g mass of Earth radius of Earth squared. And I know that this is the acceleration due to gravity on Earth. And so I'm going to multiply by 10, and I end up with 3.9, and that's meters per second squared, or newtons per kilogram. And now it wants to know what is the escape speed. Now, we'll have to get into this a little bit, how the escape speed is calculated, but the escape speed is equal to square root of 2gm all over r. So this is the escape speed equation. So this is the general equation. You can look this up, or we did it in class a bunch of different times. But if I want to calculate the escape speed for Earth, for example, it's going to be equal to the square root of 2g mass of the Earth divided by radius of the Earth. So escape speed of Earth, escape speed of Mars. We're going to use the same substitution we did down here, where the mass of Mars is 0.11 times the mass of the Earth, and the radius of Mars is 0.53 times the radius of Earth. So what this means here is that, so I'm going to take 0.11 divided by 0.53. And I'm going to take the square root of that. And I end up with 0.46 times the square root of 2g mass of the Earth divided by the radius of the Earth. Now this, again, is the escape velocity for the Earth. And what I'm then going to do, I'm going to plug and chug this into my calculator. I know the universal gravitational constant, mass of the Earth, the radius of the Earth. I think I got 5.1. Let me just check it real quick. So I got 5.1 kilometers per second. when you plug in the mass in kilometers, or when you plug in the mass in kilograms and the radius in meters, you're going to get, like 5,147, but the book reports it in kilometers, and that's the answer they got. Let's look at problem 33. What multiple of energy needed to escape from Earth gives the energy needed to escape from the moon and from Jupiter? All right. So let's look at escape velocity. So if you want to escape from a planet, for example, so here's the planet, whatever it is. It has radius r and mass m. And you want to escape. So you're going to throw a ball or launch a ball or something from here, and it's going to go out at speed v. If you want to escape, what that means is that as you're going out, you're slowing down, and v is equal to 0 when the distance here, we'll use r as our distance, is equal to infinity. So this is our understanding of how to escape, is you need to be going fast enough so that as you go, you always get slower and slower, so out at infinity, you have a velocity is equal to 0. And what this means is that when we think about the total energy, gravitational potential energy is equal to negative gmm over r, where m is the mass of the planet, little m is the mass of the object, and r is its distance. So this is how to calculate, oh no, sorry, it's a typo. So gravitational potential energy is negative gmm over r. We know that kinetic energy is always equal to 1/2 mv squared. And so if we look at these two values out here, we can see that the kinetic energy is going to be equal to 0, and the gravitational potential energy is also equal to 0. Because if you're dividing by infinity, the whole fraction goes to 0. And what that means is that the E total, which is equal to U plus K, is equal to 0. How does that manifest down here? Well, we know that E initial has to be equal to E final. So whatever energy your object has, your ball here has when it leaves, it has the same amount of energy. It just gets converted between gravitational potential and kinetic. So the initial, you're at the surface of the planet, you have some gravitational potential, and you have some kinetic. And the final is you're out here, and what do we know about the E final? Well, it has to be equal to 0. So if we now look at the textbook here, it says, what multiple of energy needed to escape from the Earth gives the energy needed to escape from the moon or from Jupiter? So let's try to figure out the escape energy. So I think what it means is, I think we're solving for kinetic energy here. So if this is true, then the kinetic energy is equal to negative gravitational potential. But what you'll notice is that the gravitational potential energy is actually negative when you have the equation here. So the escape energy is going to be equal to negative gmm all over r. And I'm using r this time because we're talking about the radius of the planet and not just an r vector, which is the distance. So this would be the escape energy for any planet. And now what we're going to do is we're going to compare the escape energy from Earth to the escape energy of the moon. So the escape energy for Earth is going to be gmm over use it for the Earth. And so the G's are going to cancel, the little m's are going to cancel because that's whatever object we're sending. And so we're left with an interesting idea here where I have the mass of the Earth divided by the radius of the Earth divided by the mass of the Moon divided by the radius of the Moon. So we're dividing fractions again, so we're going to have to multiply by the reciprocal. I'm going to rewrite this so it makes more sense. So I take mass of Earth divided by the radius of Earth divided by the mass of Mars times, or divided by the radius of Mars. And what we're going to end up with is mass of Earth times the radius of the Moon divided by the radius of the Earth times the mass of the Moon. Now, these are all values that we know. And you could look them up and plug and chug them, and I think that's probably the easiest way to go. Or you could actually write them in terms of this, like what is the radius of the Moon in terms of the radius of Earth, and what is the mass of the Moon in terms of the radius, or in terms of the mass of the Earth. So according to the internet, the radius of the Moon is 0.27 times the radius of the Earth. And apparently the mass of the Moon compared to the mass of the Earth is 0.012. So if I divide, everything ends up canceling out here, and I end up with 22.5. So that means the escape energy from the Earth is 22.5 times higher than the escape energy from the Moon. Or if I flip that over, it'll be 0.044. So that means the escape energy from the Moon is 0.044 times the escape energy from the Earth. And now we're going to do the same for Jupiter. Now, the thing is that I did it this way so we would have a larger, or so we'd have a number bigger than 1, so we understand it's 22.5 times harder to escape in terms of energy from the Earth than the Moon. So over here, I'm going to do it again. I'm going to do Jupiter. The escape energy for Jupiter, I'm going to divide by the escape energy for Earth. I have a sense it's going to be harder to escape here because it's so much more massive. But we're going to use the same structure here, where we end up with the mass of Jupiter times the radius of Earth divided by the mass of Earth times the radius of Jupiter. And I just used the same framework as we have here that we started with over here. And I'm going to plug in the values for the mass of Jupiter and the radius of Jupiter and get everything to cancel, and then we'll see what happens. According to the internet, Jupiter is 318 times more massive than the Earth. And it's 11.2 times racer. So it's a lot more massive, and yes, it is a lot bigger, but the mass is much more significant in terms of increase than the radius. So if I divide here, so it's 28.4 times, you need 28.4 times the energy to escape from Jupiter than you would to escape from Earth. All right, 39. What is the escape speed on a spherical asteroid whose radius is 500 kilometers and whose gravitational acceleration at the surface is 3 meters per second squared? Okay, so earlier in this, we solved for two things that were important. One, we solved for the acceleration due to gravity. We know that's g m all over r. So this is for any planet or object. This would be the mass, and this would be the radius. So how far you are from the center, and if you're at the surface, this would be the actual radius. The second thing that we solved for was the escape speed. The escape speed is equal to the square root of 2gm all over r. Well, I made a typo. Squared. I knew I was missing something. Now, what you're noticing here is that I have a gm over r and I have a gm over r here. And I noticed that these two things look really similar, and I'm wondering if we can have a relationship between them, where I can understand the escape speed in terms of the acceleration due to gravity at the surface. And so what I can do is I can look at this one, and what happens if I multiply both sides by r? I have rg on the left side, and on the right side I'm going to have g times r divided by r squared. And what you notice is one of these r's divides out here, and I end up with rg is equal to gm over r, which is this thing right here. So if I go to rewrite the escape speed then, I have a 2 on top, I have gm over r, but that's just rg. So if you know the escape speed, or if you know the acceleration due to gravity, you can actually use that to find the escape speed. So now I have this. And the problem says that the asteroid has a radius of, now it says 500 kilometers. We got to work in meters, so 500,000. And acceleration of gravity is 3. All right, so let's blow and chug that. And I got the escape speed to be 17,032, and that would be meters per second. B says, how far from the surface will a particle go if it leaves the asteroid surface with a radial speed, that means along a radius, not a tangential speed, radial speed, of 1,000 meters per second. So this is going to be a conservation of energy type problem. So we know that once you launch it, the energy is going to be constant. So I'm going to say that my initial energy is going to be equal to my final energy. And so I'm going to launch it. So my U at the surface plus my kinetic energy at the surface is going to be equal to my U outdistant plus my K outdistant. So the question says, how high will it go? Well, when it's at its maximum height, the final K over here is going to be equal to 0. And so I end up with negative GMM all over R. So I'm launching it from the surface. So R is the radius of the planet plus 1/2 mv squared, where this little m is the mass of the object and v is the speed that I launched it. That's going to be, it says 1,000 meters per second. That's the left side, and this is going to be now I'm going to make this r, which is going to be the distance that it goes from the center of the planet. And one of the things I notice is that all the little m's are going to cancel. So it doesn't matter what the mass of your object that you're shooting is, only that it leaves with this speed. So if I cancel out all the little m's, I end up with something interesting here. I end up with g big M all over r plus 1/2 v squared is equal to negative g big M over this r, which is your actual distance from the center. And now I got to kind of flash back over here. I'm looking for this term right here. It's gm over big R. I have that right here. So I'm going to substitute in my rg here. Don't forget to make it negative. So on the left side, I actually know these values here. So RG, it tells us our radius is 500 kilometers. So got to work in meters. Our G value is 3 plus 1/2, and it tells you that it's leaving at 1,000. That's the left side, and that's equal to negative gm all over r, where r is going to be the actual distance it goes to. Now, if I don't know the mass, I can't find this r value. I can get a value for the left side, though. So when I calculate this out, I end up with negative so negatives here are going to cancel, which is nice, but I still have to solve for r. To do that, I'm going to need the mass of the planet, and I'm wondering if I can get that from over here. So if I look back at this original equation up here, I'm going to bring it down here. They tell me my g value is 3. I know the universal gravitational constant. I don't know the mass of the planet, but it does tell me that the radius is 500 kilometers. So let's take a quick moment. And solve for the mass. I plug in the g value, the little baby g value. I know the universal gravitational constant. I don't know the mass. Here's the radius. It turns out, according to this, the mass of the planet is equal to 1.12 times 10 to the 22. I think it's an asteroid, but this is an actual reasonable mass, where this is about a sixth or a seventh of the actual mass of the moon. So that's pretty cool. And so now if I go in and I plug this in over here, let's see if I can't make that happen. So I got this r distance here to be 7.47 times 10 to the 5 meters. The question is how far from the surface. So to get the altitude, how far from the surface, I'm going to take my r distance and subtract the radius. And I got 2.47 times 10 to the 5th meters. So that's how high off the surface. The last part says, with what speed will it hit if it's dropped from 1,000 kilometers above the surface? The last part of the problem says, what will the speed, or with what speed will an object hit the asteroid if it's dropped from 1,000 kilometers above the surface? So this is similar to the last part, where we're dealing with the same asteroid here. So, whoops. So we know some things about this asteroid, but again, this is a conservation of energy problem. So we're going to let our object go, and it's going to fall toward the surface, speeding up, and wants to know with what speed it's going to hit. So we're going to go with energy conservation again. Initial energy is going to be equal to final energy. So here's the initial energy here. We have U plus K still equal to U plus K. So this is at the surface. And my picture is backward. That's going to be annoying. So I'm going to switch these. I won't be able to do it. So on the initial side, negative G all over. So this is the distance. Now this is the center to center distance here. And don't forget that our planet has radius r, or our asteroid, or whatever it is. And it says we dropped it, so that means initial kinetic energy is 0. So that's cool. And at the surface, the gravitational potential energy is gmm all over r. And this is 1/2 mv squared. And this is the speed that we're solving for. And so I can look at this a little bit more. Again, all the little m's cancel, so it doesn't really matter. So I'm left with negative g big M over r plus 1/2 v squared is equal to negative g m over d. So 1/2 v squared is equal to so in this case, we have r plus h here because it was released from some height, which we know, I think it's 1,000, right? So I think we know everything that we need to just plug and chug this. So let's see if we can do that. So we know our g value. We know the mass of the planet, 1.12 times 10 to the 22nd. And the radius of the planet was 500,000 meters. And this r plus h was 500,000 plus, it says it was released from 1,000 kilometers. So let's plug and chug this. So I plugged and chugged it. This right side multiplied by 2, took the square root, and I got v is equal to 1.411 times 10 to the third meters per second. That'd be 1.41 kilometers per second. All right, that is the end of problem set 1.